Towards the beginning of the 20th century, David Hilbert, a great mathematician, envisioned a great program for mathematics. He wanted to place all of mathematics on a solid, complete, consistent, formal foundation. He believed that every mathematical truth could, in principle, be derived from a finite set of axioms using logical rules. However, in 1931, more or less during that time, so in the early 20s and early 30s, we had another great mathematician, or if you want, a logician, not just a mathematician, but also a mathematician interested in logic. Kurt Gödel shattered Hilbert's dream with his own famous incompleteness theorems. He proved that any formal system strong enough to describe basic arithmetic is either incomplete, meaning that there are true statements that it cannot prove, or inconsistent, where contradictions can arise. So Gödel's work revealed intrinsic limits to formal systems, forever changing the philosophy of mathematics. And in this quick video, I would like to cast some light on Gödel's concept of incompleteness. So what is the idea behind this incompleteness? And first, let me just start with some very basic definitions without getting into the strong formalisms that we might find in logic. So I will not write down very formal sentences and so on. So I will try to stick to the basic principles, just showing the basics of this beautiful logic that Gödel discovered. So let's start with the definition of a formal system. Let me write it down. Formal system. So a formal system basically is a system with precise rules for creating statements and proofs. One example is the so-called piano arithmetic. So, but apart from the examples, we have to think of something that makes the rules for creating statements and proofs. The basic rules are, for example, axioms. So we have to start from a set of axioms that we have to use because we have to start from something. In mathematical theory, and even in physics as well, we have to start from some solid background that we can use to build, or let's say to deduce something. So we have axioms, and then we have mathematical operations like addition, subtraction, multiplication, division, which of course can be seen as different sides of the same coin. So multiplication and division are related to each other. So if we multiply something by 7, it is like dividing the same thing by 1/7, for example. So if we divide the number, let's say 8, by 1/7, this is equivalent to multiplying the number by 7. So there is a relation, as you can see. And similarly, addition and subtraction, they are also related because, for example, if we add two numbers, let's say 7 and a negative number minus 8, and this is equal to 7 minus 8. So we can view a subtraction as an addition as well. So there is some kind of relation between these operations. But anyway, we have a set of rules, a set of mathematical rules, a set of axioms that can be listed in a certain manner. And then we have some other features, some other characteristics that the formal system might have. For example, consistency. So consistency, let me write it first. If the system is consistent, it means that it is possible to derive, for example, some statement A, and let's assume that this statement is true. Then it means that its negation, so let's say not A, which, for example, can be written down according to some formula. So when I say statement A, this might be intended in a general way. So we have a formula, for example. If the formula is true, the negation of that formula is false. A simple example might be a certain variable, let's say x, which can take only the values 0 and 1, so it's a binary number. If we can prove that x is equal to 1, then it means that its negation must be 0. So this has to do with consistency. Then we have other features. For example, we have probability. Probability means that if we want to prove that a certain statement A is true, we have to start from the axioms. So we have the axioms, and then using the mathematical operations, we want to show that this is true. So it means that A is provable. These are the basics that we need. Then another concept that we need is the so-called Gödel numbering. So what is Gödel numbering in a nutshell? So Gödel assigned a natural number to every symbol, formula or proof, and even a statement in the system. So it's a way to start from, let's say, a formula or a statement, and then, according to some kind of algorithm, we associate the statement or the formula with a number. Let's say a number G1, a number G2 for the statement, and so on. And this kind of relation is unique. So it means that if we have G1, this is associated to this formula. And similarly, if we have G2, this is associated to the statement. Now, this is actually very important because we are able to do operations on numbers. And these numbers are associated with, for example, a sentence, which can be a statement of any kind, or a formula. So we are able to do very different things, but by staying in the realm of numbers. So this is the importance of Gödel numbering. And now I want to give you a simple example. So for example, let's say that we want to describe a simple operation, a simple formula, like this: 0 plus x equal to x, let's say. And we can associate the number 0 to a number. So this is a number 0, but I will associate it, for example, with the number 1. So this is already a number, but I will associate it to the number 1. Then what about the plus? So we also have the symbol plus that we need to convert into a number. So the plus will be converted, for example, into a 2. And then we have x. X will be converted into a 3. We have also the equal sign, which will be converted into a 4. So this is some kind of algorithm that I want to construct, which seeks to convey the logic behind this. So it's not the only possibility. The algorithm might differ, but the uniqueness remains. That's the importance. Then we also have this x, which we have already encoded with the 3. So for example, 0 plus x equal to x would be a sequence of numbers. In this case would be 1, 2, 3, 4, 3. And this is not actually the number that Gödel creates. He uses a prime exponentiation, so using prime numbers, and this is actually the key to Gödel numbering, using primes, because primes have special properties that allow converting the sequence of numbers into a single natural number. And I will not get into the details of primes. The mathematics behind prime numbers is very large. There is an abundance of literature on that and theorems and so on that I don't want to get into. And it would be way beyond the purpose of this video. But let's say that the first set of prime numbers is the following. So we have 2, which is the first prime number, then we have 3, then we have 5, then we have 7, then we have 11. So these are the first 5 prime numbers. Then what we do, we want to simply take the first prime number and then raise it to this first number here, 2 to the power 1. Then we take the second one and we raise it to the second number, which is 2. Then we have, you understand the game, it's 5 to the third, 7 to the fourth, and 11 to the third again. So we have another 3 here. Then we might multiply these numbers, and what we get is we obtain some number g. We obtain some natural number. This will be a natural number, and it will be the Gödel's number. At this point, what Gödel does with this kind of numbering is he wants to construct some sentences, and he wants to study the nature of the sentences, the properties of the sentences. In particular, Gödel creates a sentence of the following kind. So we can write G, which is a Gödel number, equal to the following statement. So it coincides with the following statement. G is not provable. So basically, Gödel wants to encode such a sentence using the encoding that we have explained there. So it's Gödel's numbering. If we are able to encode such a sentence, well, we have a problem actually. We have some problems. In particular, if G is provable, we have a problem because G proves that G is not provable. So if G is provable, we are running into an inconsistency. So it means that the system would be inconsistent. On the other hand, we might have that the system is consistent, so we might have consistency, but if we have consistency and this sentence is correct, then this sentence cannot be provable. So G is not provable, which is consistent also with this sentence. G is not provable, and anyway, it means that the system contains something that is not provable. So this is also related to incompleteness. It means that a certain mathematical frame, let's call it that, even if it is not precise terminology, in a certain mathematical frame, there is some incompleteness. So we might have either provability or inconsistency. And this is just the surface of Gödel's incompleteness theorems that I wanted to show you. And of course, there is much more to it than meets the eye, but I just wanted to get the main ideas across.